First up, we have Dr. Leonardo Guimarães from UFPE. Please come on up.
So, thank you, Andrew, and it's a great pleasure to be here again for this summit, and a privilege to have to be here in this year where a lot of discussions in problems that is in our near future in Brazil. I will talk about one of the main topics of my chair, that is the interaction between reactive transport and geomechanics, when we have, for instance, a long-term injection of CO2 that will that can dissolve the rock and can affect porous permeability, but also geomechanical properties. Is a point of concern that we discuss as people in the industry, both for injection of CO2 for EOR or injection of CO2 for CCS projects. So the idea is to build models based on experiments that will honor the behavior of this coupled phenomena. And I'll try to show you that the model can be a little more complex than elastic, and in fact that you have to use elastoplastic with a chemical variable as a state variable for this mechanical behavior. And well, this is our integrated lab in Recife, Brazil. That now, since last year, is an institute. We have about 12 labs in different areas related to oil and gas industry. And of course, we have geomechanics and geology and reservoir simulation that are the teams related to this chair. And so we are here in Recife, Pernambuco, Brazil, in the northeast part of this country. And I would like to talk about a little bit the scenarios that we have related to energy. Well, if you see this red circle, it's the northeast region. And in this part of the country, we have a very dry region, a little bit far from the coast. And it's almost a desert. So we have a lot of wind and light. So we have already huge production of renewable energy. And we are in the beginning of green hydrogen. So green hydrogen today is a very important topic in Brazil. And the production is, everyone is talking about production, but very few people is talking about storage. So this is very interesting. So it's an opportunity. We are already in contact with companies that are interested in store hydrogen in salt caverns that we have onshore salt caverns in this region. Again, we have in the coast, we have industries. For instance, in our port, we have a refinery, thermal plant for electric generation, energy electric generation. So we have production of CO2, and also there are discussions about CCS. And if you are going to talk the companies, oil companies in Brazil, about research in projects, it's like, let's do something in geomechanics. Okay, let's do something geomechanical, but for CCS projects. So CCS projects are also a very important topic in Brazil. We are not injecting CCS, CO2 for CCS yet, but we have lots of pilots that are already announced. So in the near future, we expect to have pilots on CCS, the first pilots in CCS, and we expect also storage of CO2, of hydrogen in aquifers and saline rocks. And another aspect related to this region is that we have depleted gas reservoirs. So in general, we have a very nice opportunity. And again, another aspect is that we have a new Brazilian legislation for CO2 emissions that is coming, probably this year, that is compelling the companies to achieve the net zero carbon emissions and all these aspects. It's for one side. For the other side, we are still increasing our production, our oil production. So it is expected to have a very, we are going to extract oil and gas for a long time. So you can see here in brown the post-salt production. Then in pink we have the pre-salt. So it's still increasing the production, and at least it will be kept in this level. And with the pre-salt reservoir we have in this part. I'll try to. In this part, we can see the production of CO2 that comes from the pre-salt. And by environmental laws and restrictions, all the CO2 must be reinjected as a EOR strategy. So we are not injecting CO2 for CCS, but we have an experience of more than 10 years of injecting CO2. In fact, it's a kind of carbon utilization as IOR, and 25% of all global CO2 injection is in the pre-salt. And so we have this concern, injecting CO2. CO2 can dissolve in the water, and we have acidification, and then we have dissolution of minerals that will affect porosity, permeability, and change the properties of the fractures and geomechanical properties of the rock. And this is the research interest that we have. And the chair is the main topic of the chair. So we proposed 3 years ago apply this to work in this problem for both IOR and CO2 injection for CCS. But just now I will have the opportunity to apply in CCS because it's now becoming a reality there in Brazil. And the ingredients of the chair, the title of the chair is reservoir modeling and robust optimization, and the ingredients are outcrop characterization. We have geologists in our team, upscaling, geomechanics. By the way, we have a poster that is presented by Aline in a submarine landslides in a very important field in Brazil. That can be, you have to do some slope stability analysis. So check the poster, it's a very interesting project. And also laboratory testing, constitutive modeling, that I'll talk about this here. And also log optimization, uncertainty modeling, machine learning. We have a new project as well with Petrobras, with optimization with machine learning that Alexandre presented in this session posters as well. So in this problem, this is a previous work that I showed you a few years ago, that we have this edometrics test that we apply a vertical load, we inject a fluid that will dissolve the rock, and we are able to measure the lateral stress as we have the restrictions to the lateral displacement. So you have in the decrease of the size of the sample, you have a loss of compression of the sample, and we have the decrease of lateral stress due to mineral mass dissolution, and after that rearrangement of the internal granular structure, you have the increase of the stress, a tendency of dilate, that as we are restricting the displacement, we have the increase of lateral stress. Okay, so we can establish a chemical-induced deformation that is a function of the total mineral volume. So you have to run, in a finite element code, you have to run the reactive transport behind this to get this total mineral volume, and if it changes, we can induce deformation to the model. And if you inject a reactive fluid, you can see here the front of the solution, and where the mineral remains, we have higher vertical stress, we have a non-uniform stress in the sample, and you can model this, and we can obtain, for instance, this in the model, this decrease of lateral stress. And if we consider elastoplasticity, a very simple molecular model, we can introduce this envelope. And if we introduce a softening, so when the Morse cycle reach the morculum, and you have a softening, so we come here, and the only way for the lateral stress, horizontal stress, is to increase, so we can have this increasing of lateral stress. Sorry. But unfortunately, it's not enough. We can do this qualitatively, but it's too simple to simulate this. We cannot have a good correlation for more than one test. So we decided with Katia, is a PhD student that finished this year. Her work is already published. And we begin a experimental program with this kind of test. We're using synthetic carbonate rocks, more or less porous rocks, that we inject an ACE from the top to the bottom, from the bottom to the top, and again with under vertical load, and we can measure lateral stress. And we could observe that we have dissolution of the material, and we have much more pores. It's a CT scan analysis, and much more connected pores. And this time we used a critical state model that this model has the shear envelope here, but also have this cap that is the locus for the pore collapse. So in this case, we have this model has two yield surfaces that we define the region where the deformations are reversible. And we have a yield surface for the bonded material and a yield surface for the unbonded material. And when we have the degradation of chemical degradation, we are going to affect this yield surface, and when you have mechanical degradation, we are going to affect this yield surface. So we have the possibility to include degradation of the bondings, the cementation of the mineral due to mechanical and chemical actions. And so we introduce a pre-consolidation stress, that is this point that controls the size of this yield surface, and that depends on a chemical depends on the chemical degradation variable that at the end depends on the cement concentration. So again, we have to run together with the reactive transport problem, the geomechanical problem. We have to run with the reactive transport problem to get the mineral concentration and then update our yield surface. And okay, so with this model, we implemented a fully coupled finite element code that we developed, and we can now have very nice results with the test that she performed. So we can see the increase. In this case, we have only the increase of the lateral stress in the sample, the model, and it's good enough for us because it's a lot of phenomena are happening, and it's for us is a good result. And we have the volumetric strain evolution, so the sample, we have the decrease in volume of the sample. And again, we have the decrease of this variable that is the bonding component of the pre-consolidation stress. So you have a chemical softening of the material, But in fact, we have an increase of the pre-consolidation stress for the unbonded material. So we have a mechanical hardening. What happens is that we have this surface is shrinking. This yellow surface is shrinking, and the internal surface is expanding. And so you have chemical degradation and pore collapse. And you also have the decrease of tension strength of the material. So we are happy with this, but it's not enough, unfortunately. Okay, we could obtain a very good stress path of the sample in the compression and shear space. So we can see here that the stress path during the test is the decrease of shear strength and increase of compression. And this is due to the decrease of elastic domain of the samples as it loses its cementation. So the initial yield surface is this one. So when you have the shrinkage of the yield surface, the stress state have to move from this point to this point, decreasing shear stress and increasing compression. So it's elastoplastic mechanisms that is triggered by the chemistry. And so as I was mentioned, we are not there yet. There is an important aspect that we have to implement in our model that is related to stiffness of the material. When we expose the samples to acid solution, we have the decrease of the stiffness, but sometimes it's not intuitive because you can see that all the samples with different acids decrease the stiffness here. But if the acidification is too aggressive, we have the formation of wormholes, and so all the other parts of the material will not be degraded, so the flow will be concentrated to the wormholes. And in fact, the most acid, the pH 2 solution, it has less degraded than pH 4 and 3. So it's complicated because you have to include chemical damage depend on the Cooler number. Then the Cooler number controls the formation of wormholes in the sample. So it's interesting because if for low Cooler number, you can have the damage area very close to the well. And for higher Cooler numbers, you can have the wormhole, and then degradation will be a little bit far from the well. So the way that the chemical attack will happen depends on the rate of the injection of the reactive fluid. And yes, so it's in progress, and we have a new project with Petrobras. All this project is only experiments, but we are going to use these experiments to improve our model. In this case, it's Victoria. She was in the poster, and she's in charge of this project. We are using acidification of Indiana limestone. Now we are working with natural carbonates. And the idea is to inject acid solutions and to check now using a triaxial test how this degradation can take place in more realistic rocks. We are going also to use rocks from outcrops, and because in the next work that I will show, the composition of the carbonate will affect a lot the acidification. So, Katia did also work in fractures. So you can see that the fractures increase the aperture when we inject an acid solution. And in previous work done with natural carbonates from outcrops, this PhD student, Shirley, she injects in a fracture acid and shear the fracture. And we can see here that channels are formed when for the fractures. So in the peaks of the faces of the fracture are not dissolved. So what we observed, the final conclusion of this is that for this test that she performed, the mechanical shear is much more effective in the degradation of the shear strength than the chemical attack. And in the poster section that Jimena presented, she was to KAUST to perform another type of shear test, where we injected in the center of the sample in a tube, it's a well that injects acid, and we can have the flow of the acid solution from the center towards the outside of the sample. And it's very nice equipment. This equipment was designed by Carlos Santamarina, that's now is in Georgia Tech. And but the collaboration was with Thomas Finkbeiner and from KAUST and Alejandro Cardona from Texas University. And we have with the equipment we can have normal stress, shear stress by torsion, and injection of acid. Okay, I will not have time, but I just mentioned that Jimena shows very similar qualitatively results as the previous work. We have for Ruth, she tested smooth and root fractures, and you can see channels that forms in both types of roothness. And we have also the effect of the load and unload much more important than the acidification for this test as well. So the transmissivity enhancement due to chemical treatment is mainly on surface with pre-existing roothness and in the rock with grain-supported texture, more than samples with fine-grained matrix and smooth fracture surface. And well, some conclusions. Well, I will be quickly here in the conclusions. We validated a critical state theory for degradation of rocks, matrix rocks, using bonding variables, but we have to improve these models, considering damage in this degradation of the stiffness. But formation of wormholes is increase the challenge to do this, and we have to study more carefully. So for this reason, we are going to natural rocks. Is the project that we have. I showed you. And in the fractures, of course, mechanical action, such shears and compression, seems to have great impact in comparison to the impact of chemistry. And the composition of the rock is another aspect. Jimena tested 3 types of rocks, different compositions, and has an influence on the behavior of the fracture. And we are on research in progress. We are doing some modeling using phase field models, as one proposed by our colleagues from KAUST, that can do also the dissolution of the fracture, and is able also to study the crystal growth. That is the behavior of the fracture, and we have crystal growth. That is a problem that, as we see in the presentations, is very interesting for CCS as well, when we have precipitation of minerals. And okay, thank you for everyone and for the sponsors.
Thank you, Dr. Guimarães. Questions from the floor as well as online, please.
Thank you, Leonardo. This is quite impressive, the study you have done. And I have obviously questions about impact of hydrogen that we are studying on the rock properties. And
yes, it's a new field that we can collaborate.
And also, Rick asked me yesterday the question about
yes.
the shale rock, and also
exactly.
the main question there is, would hydrogen yes. alter the properties of the rock?
Yes.
And if so, what would be the right way to study that?
Exactly.
Okay, so
We would love to do this kind of work also to check the effect of hydrogen.
okay. Thanks a lot. And the second would be about the scaling up of all these geochemistry in the lab to the field scale, and how would they be predictive enough when you change the scale and the heterogeneities and all the
Exactly. Well, the way that we have is to perform. We are not performing yet. We are in the formulation of the constitutive models. But the next steps to beginning to simulate the field scale, at least the near field from the.
But given the rates that you find in the lab, or the alteration of the mechanical properties that are done on samples that are perhaps some sort of centimeter scale, and then putting what Sebastian was mentioning about 100-meter type of grid blocks.
It's a change. It's just it will be a challenge. Yes, for sure.
Good. At least we have the same challenge. So that's good. So, thank you very much.
Thank you.
Okay, I have a question. Conclusion number 1. Your critical states theory, in this case under odometric conditions, could that be expanded to consider lateral movements and true stress states? You can go back. Like you say elastic plastic model on using critical state theory that's based on constant vertical stress and 0 lateral displacement.
Yes, it's because of the experiment, but we can generalize. It's general. It's 3D. It's a completely 3D model that you can apply to any kind of stress state.
Right.
It's completely general. Yes.
Now for current, I guess geomechanics components of reservoir simulators, they have this classical Cam-Clay model, Drucker-Prager plasticity model.
The Cam-Clay model is the one for unbounded material. The base of this model is Cam-Clay.
Okay.
So we can, when we expand this, so it's not Cam-Clay, but it's based on Cam-Clay. Yeah.
Okay, can be modified to
it's a modification of Cam-Clay model to include cementation. Yes.
Okay. Yeah. Wonderful. Okay. No more questions. Thank you, Dr. Guimarães.